Okay, 5.2 and 5.3. Testing 1, 2. Okay, good. We're live. Okay, 5.2 is on growth and decay. And we've seen growth and decay before, but now we're going to talk about the area under growth and decay models. So under the growth and decay models. So we're going to take the integral of some growth and decay models here. Okay, so total growth, okay, of a growth model, okay, or what we would call an exponential model, right? Total growth would be from 0 to t, for wherever I stop, interval from 0 to t of p naught. P naught is the initial amount that I have, e to the kt, okay, dt. And so when I integrate this thing, let's see what we get. We could pull the p naught outside, and I get the integral from 0 to t of e to the kt. Okay, so now everything here is a constant. Sorry, did somebody have a question? Okay, everything here is a constant except, go away. Okay. Except the t, the small t, the little t, not the big T. Everything else is going to be treated as a constant. Okay. Okay, so when I take the integral, this is kind of like a u sub in a way. If I do a u is equal to kt, then I would do du is equal to k dt, or divide by k, and I would get du over k is equal to dt. Okay, so now I can do a u sub on this thing. Okay, I'm gonna keep my limits the same for now. Okay, so 0 to t of, this is going to be e to the u du over k. Okay, so e to the kt gets replaced with e to the u and d to the u k. Okay, so what's the integral of e to the u? Well, it's just e to the u. So this becomes e to the u. Okay, I can pull this k that's being divided, I can pull that out, and I get p naught over k. I get e to the u. And then I want to evaluate that from t to 0. But I have to evaluate on my original t. That's the small t, which is what I integrated on. Okay, I can't integrate on u. We don't want to integrate on u. Okay, or evaluate on u. Okay, we want to evaluate on t. Well, what was this? This was p naught k over k e to the kt. Okay, now we can evaluate from 0 to t. I'm going to plug in t. Okay, t in for t. Okay, big T in for little t. And so this becomes p naught over k e, okay, to the k big T now. Big T is where I stop. It's the time that I stop. Okay, and then minus p naught over k e to the k times 0. Okay. Okay, so well, let's see how we can clean this up. Let's factor out a p naught over k. Okay, I'm going to get e to the kt minus e to the k times 0. Well, that's just k times 0 is 0, right? So this is e to the 0. But what is anything to the 0 power? Well, it's 1, right? So this really just becomes 1. And so that is my integral. This is the integral of 0 to t of e to the kt, sorry, p naught is in there, p naught e to the kt dt is equal to this. So we never have to do this again. This integration, we know exactly what we're supposed to get out when we have this growth function. And this is my growth function, right? Remember this function? P equals P naught e to the KT. That's like my PERT account. That's population growth. That's just exponential growth, right? That's continuous exponential growth. What does that look like? Well, it looks like this, where we start out at a certain value, P naught, and we end up at a certain time, T, okay, and that tells us, okay, at a certain time, T, well, we'll just leave it like that. We're gonna end up at a certain amount, right? But what if we wanted the total of all of that, of all those amounts, right? The total of what we call the accumulated amount. Well, we take the integral under this, and the integral under that is going to be this amount here that we calculated out. Okay, so we call this the accumulated continuous growth total. It's the accumulated continuous growth total. Right? Okay, we could go through a similar procedure. I'm not going to do it just for the sake of time. Where's my people? Okay, for the sake of time, we could go through the same procedure if we had decay. If we had decay and it went out to t, okay, we could go through the exact same procedure we did before. What would be the decay model? Well, the decay model here, so this guy is this one, and this guy, the decay model, is going to go P is equal to P naught e to the negative KT, right? So yeah, let's see what happens here. Okay, so decay is going to have a negative, and so when I integrate this 0 to t, okay, P naught e to the negative kt, okay, dt, we get out, if we were to go through all the work of integrating this, we would get out P naught over k times 1 minus e to the negative kt. Okay, so we get a negative in there, and so we have to kind of flip the order around. Okay, and so we have this as our accumulated decay total. So this is my accumulated decay or continuous decay. Decay total. Okay, so that's our accumulated continuous decay model. Okay, so how does this apply to the world of business here? Okay, let's talk about the future value. Okay, future value. Okay, so the future value is, okay, P of t, okay, is equal to, P of t is equal to P naught e to the kt, okay, when this thing is my future value. When we're talking about growth, that's our future value, and this is my present value. Okay, and then this is my rate of growth. Okay, so future value, rate of growth, and then T is time in years. Okay, so T is time in years. Okay, so let's do an example here. Okay, in 2000, world production of gold was 2,700 tons of gold, and it was growing exponentially at 0.98% per year. Okay. If growth continued at this rate, over the next 8 years, how much gold was produced from 2000 to 2008. Okay, so it's saying that we have our gold population growth. Okay, P naught E to the RT, we could call it a rate, R or K, it really doesn't matter. Okay, so either way. Okay, and we want the accumulated amount. See, we don't want the amount at 8 years. Okay, it's saying that at time zero, we're doing 2,700 tons. But then we're saying it's going to grow, right? It's going to grow exponentially. And then we're going to be at some point after 8 years, right? So at T equals 8, we're going to be at some amount. Well, I want the accumulated amount, not just the amount at 8. Does that make sense? Okay, so that means that I'm going to have to do my integral from 0 to 8 of P naught, which is 2,700, okay, E to the 0.0098, that's 9.98%, T, okay, and we saw that this equals P naught, okay, over K. So P naught was 2,700 using the formula, right? So we said that 0 to T of P naught E to the KT was equal to P naught over K times E to the KT minus 1. Okay. So this is going to be 2,700 over K, which is 0.0098. Okay, times E to the 0.0098 times T, which is going to be 8 minus 1. Okay. Okay, so all we have to do is plug that into a calculator correctly. And we should get, let me share my screen here. Okay, we should get whatever. Okay, so we should get the correct number of tons, right? Okay, tons of gold. Okay, so we have 2,700 divided by 0.0098, okay, is equal to that. And it's going to be times, parentheses, E raised to, okay, E raised to the parentheses, 0.0098 times 8, close parentheses, okay, minus 1, close parentheses, equals, look at that, 22,469. Okay, so about 22,400, about 22,469. Okay, tons of gold. Okay. Okay, let's see how this works with money. Okay, what is the future value of a continuous income stream okay, at a rate of $3,650, okay, per year, okay, invested at 5% for 3 years. Okay, so okay, we have a continuous income stream at a rate of $36.50 per year, invested at 5% for 3 years. Okay, so what this is saying is that this is saying that we are investing, okay, $3,650 per year. However, that $3,650 per year comes in continuously. So we start off with nothing, okay, and then it comes in continuously until I hit $3,650 at the end of the year. At the end of the year, I'm at 3,650. Okay, and then I keep going, and it keeps increasing. Okay, until I put in another $3,650 by the end of the second year. Okay, so this is another $3,650 put in, so this is year 1. This is year 2. Okay, and then, right, so then it continuously goes in up until year 3. So now, however, okay, I'm putting in money continuously. I'm continuously dropping in money, right? But the money that I'm making, the money that I'm putting in, say I put in a penny on the first day, that money that I'm putting in is making interest. Okay, so the accumulated value of this for 3 years is really the area under this curve. Okay, it's the area under the curve of investing each of these, right? So here's how this works. Okay, so think about what I want to talk. So the accumulated value is going to be bigger than the sum of just plopping in 3,650 each year. If I did 3 times 3,650, okay, I wouldn't be making as much money. Right, that would be with 0 interest, right? So 0 interest, at the end of the first year, I'd have 3,650 in the bank. So that's $10,950. Okay, if I earn 0, this is 0% interest. Okay, so what would happen if if at the end of each, say the end of each year, I just put in 3,650, right? So let's think about what would happen. But now it's at 5% interest, but only putting money in at the end of each year. Okay, only at the end of each year. So you're making nothing on the first year. You've made nothing. This is 0. Okay, so from 0 to 1, you've made nothing. Then what happens? Well, I plop down $3,650, and then I start making money on that $3,650 for the first year. And then what happens? Oh, I increase, let me move this up. Okay, I increase by another 3,650. So this here, this is my right. So then I increase by another 3,650. This here, I'll do like that, is $3,650. Then I make money off of everything, the interest and the principal of both of these. I make money in the 0 to first year, I made nothing. From the first to second year, I made interest off of what came in the first year. On the second year, I make interest off of what came in the first year, second year, and the interest made off of the first 3,650. And then in the last year, I would just plop down the extra $3,650. That made nothing. That made 0 interest as well. Okay, so this is what we call an annuity, where we're dumping money in. Okay, so this is an annuity where we're dumping money in annually. Okay, and we're saying, we're gonna dump in money here. We're gonna dump in 3,650. Then that's gonna make interest, and then I'm gonna dump in another for year 1. This is actually year 0. We've dumped in nothing for year 1, and then for year 2 we dump in this one, and then we just keep dumping in 3,650 into our bank account. Okay, so if I did this, okay, I would really be looking for the area under these two as my accumulated wealth. Okay, again, that's going to give me less than if I just started continuously dumping in money in the very beginning. Okay, if I broke up that $3,650, okay, and we could calculate this out, how much this is. Okay, and how much this comes out to be is $11,400 $521.01. All we'd have to do is calculate the area under these two curves. Okay, but that's what it comes out to be if I broke it up like this. However, that's not going to make me the most money. The most money is actually going to come, okay, from what we call the accumulated future value of a continuous income stream. Okay, continuous income stream. We want the income stream to be continuous. We want it to keep, accumulating. We want this 3,650 to accumulate because it's not going to be actually 3,650 that it accumulates to. It's going to be actually a little more, right? Because all of this interest is also accumulating money in that first year. It didn't make us nothing. Okay, we said, oh, okay, we're going to accumulate to that amount at the end of the first year. Okay, and we're going to accumulate to that amount at the end of the second year. We're going to dump in, okay, our 3,650, and we're actually going to make more money by having interest being paid on the little amount that's trickling up. Okay. Okay, so the accumulated future value of a continuous income stream is represented as A for accumulated value is equal to 0t R of t, where R of t is going to be P naught, basically. Okay, that's R of t is going to be my function that's telling me over time how much am I putting in. These are my deposits. Okay, and if all the deposits are the same, then you'll see that this defaults back to something really nice. Okay, and this is e to the k. Okay, k of t minus big T minus little t. Okay, so if we were to integrate this thing, okay, we would actually see that if R of t is a constant, like $3,650, okay, if R of t is a constant like $3,650, then A defaults to this. It defaults to R of t over K, or we just call it R in that case. It's just R because it's just a constant. Okay, R over K times e to the k t, big T, minus 1. It defaults back to our accumulated population growth formula. Okay, this is for accumulated wealth. Okay, when we have continuous deposits, those deposits are coming in continuously. Okay. Okay, so let's calculate how much money we would actually make off of this. So in our case, what's R? R is 3,650. What's K? K is our interest rate. Well, that was 0.0098. Or sorry, it's not 0.00. It was 0.005. It was 0.05. It was at 5%. Okay, and then what was our, well, everything else is after how many years? Well, this would be after 3 years, right? So e to the k, which is 0.05 times 3 minus 1. Okay. So let's plug that into the calculator. Clear. We get 3650 divided by 0.05 is 73,000. Okay. So this is 73,000 times e to the 0.15 minus 1. Okay. So times e to the 0.15 minus 1, close parentheses, equals 11,813.90. 11,813.90. Okay, so we made more money because we're continually making interest off that. Okay, let's flip it around and let's talk about present value. Instead of future value, let's talk about the accumulated present value. So accumulated present value of a continuous income stream. Stream is, okay, we call this B, is equal to integral 0 to t of r of t e to the negative kt this time, dt. Okay, if we were to, where r of t is the amount per year of the income stream and income stream period. If r of t is a constant, we'll call it r, just a constant r. Okay, then b is equal to r over k of 1 minus e to the negative kt. So it's that accumulated exponential growth. Okay, so accumulated exponential growth. Okay. Okay. Let's do last example here for this section. Okay, find the rate per year of an accumulated income stream if it has present value 53,000. No, it's just it's accumulated present value. Okay, it has present value. B is B. Okay, 53,259. 18.18. Okay, so what are we looking for? We're looking for the rate per year, or the amount per year, or the amount deposited per year. We say the amount deposits. Find the deposits per year of an accumulating if it has present value of this thing. Okay, invested at 3.5% for 18 years. Okay, so it has this present value. Okay, and so let's find R in this case. So B is equal to R over K of 1 minus e to the negative kt. Okay, big T. Okay, that should be big T. Capital T. That's good. capital T is my stopping time. Okay, so what do we know? We know that this present value is 53,259.18. I'm looking for R because I don't know what R is. Those are the deposits per year. Okay, we're going to assume that they're all the same. Okay, they're constant deposits. Okay, over K, which is 0.035 times 1 minus e to the negative 0.035 times t, that's the accumulated number of years, that's going to be 18. Okay, so the first thing I want to do in solving for R is I want to multiply both sides by 0.035. Okay, so multiply both sides by 0.035. That gets rid of this thing that's being divided, right? And then we can actually divide by this thing over here, 1 minus e to the negative 0.035 times 18. Divide that out, and we would get r. So this is 1 minus e to the negative 0.035 times 18. Okay, and so r would be whatever this thing is. Right here would be this thing on a calculator. So I'd have to probably do the top first and then the bottom. So let's do that. Let's do the top first. So uh, 0.035 times 53,219.8 or 259.18. Okay, is 1864.07. 1864.07. Okay, nice. Okay, so divide that by 1 minus e. What's 0.035 times 18? 0.035 times 18 is 0.63. So this is e to the negative 0.63. Okay. So let's take our 1864.07 and divide it by 1 minus e raised to, okay, 0.63 negative, okay, close parentheses, equals, okay, is $3,988.10. So $3,988.10 would have been our deposits. Okay. On that income stream. The income stream would be that amount per year. Okay. Okay, that's it for 5.2. Let's jump into 5.3. Okay, 5.3 is improper integrals. Okay, or integrals that go to infinity. Integrals that go to infinity and beyond. Okay, integrals that go to infinity and beyond. Okay, so the main idea here is that if we have an integral that goes from, say, a to infinity of f of x dx, then we could say that this is the same as the limit as b goes to infinity of the integral of a to b of f of x dx. Okay, so that's all we're saying there. We're just saying that that's going to be the limit of the integral itself. Okay, that's how we deal with improper integrals. Okay. Okay, if the limit exists, the limit exists, then we say the interval converges. However, if it does not exist, then the interval diverges. Okay, it diverges, either converges to a value or it diverges. Okay, so if I have something that looks like this, that's going to converge to an amount. As I go to infinity, this thing's going to go to 0. Okay, if my f of x goes to 0, then I know that it's going to converge. Okay, if f of x goes to 0, then the integral converges. Okay, if this thing gets bigger, however, say that it goes like this, okay, and it gets bigger and bigger and bigger and bigger, I'm just going to be adding more and more area as this thing goes to infinity, right? Okay, this thing goes to 0. That's going to go to infinity. I'm just going to be adding more and more area under that curve. I'm just going to be piling up. So this thing, this interval diverges. Okay. Okay, so let's look at our first example here. Determine if the integral is 0 to infinity of 4e to the negative 2x dx is convergent or divergent. Convergent or divergent. And if convergent, find its value. Okay, so this thing does converge, but let's just see why it converges. Okay, so we're going to say that the integral from 0 to infinity of 4e to the negative 2x dx is the same as the limit as x goes to infinity. Okay, oh no, so as b goes to infinity, not x, as b goes to infinity, from 0 to b of 4e to the 2x dx. Okay. So now we're just going to integrate this thing here. Okay, I'm going to say, oh, okay, well, what is this? This is a u sub. So u is equal to negative 2x. Du is equal to negative 2 dx. So divide by negative 2. Okay, and so this goes from 0 to b of 4 e to the u du over negative 2. Okay, well, the integral of e to the u is just e to the u. So this is 4 over negative 2, which is negative 2. That becomes negative 2. Okay, and this is just e to the u, evaluated from 0 to b. However, I need to plug in what was my u. My u was negative 2x. So this is negative 2, okay, e to the negative 2x evaluated from 0 to b. Okay. And so now I'm going to plug the b and the 0 in and see what we get. Negative 2e to the negative 2b minus negative 2e to the negative 2 times 0. Keep close attention to your negative signs. Okay. And so this thing, I'm just going to let be negative 2e to the negative 2b, okay, plus 2, and then this is e to the 0, but what's anything to the 0 power? It's just 1, right? It's 2 times 1. This is e to the 0, which is 1. 2 times 1 is just 2. Okay, and so we want to do the limit as b goes to infinity of this thing. Well, does the limit exist here? Let me rewrite this. This is the limit as b goes to infinity of negative 2 over e to the 2b. Okay, a negative exponent is positive if I bring it down below. Okay, and then plus 2. Now, what happens when I plug in infinity here? Well, that becomes 2 over infinity, and anything, any constant over infinity, this goes to 0. So this, the limit here does exist. Okay, the limit as b goes to infinity of negative 2 over e to the 2b plus 2 is equal to 0 plus 2, which is equal to 2. So the limit did exist, and what does that tell me? Okay, that tells me the original function, f of x equals 4e to the negative 2x, was a convergent function, and the integral from 0 to infinity of 4e to the negative 2x is equal to 2. Okay, so really, what is this telling me? Okay, remember, this was an exponential decay function, right? The exponential decay function with a value of 4 at the very beginning. P naught is equal to 4 here. And so this is going to decay, and it's going to decay very fast, okay, because of this negative 2. And so does this thing converge? Yes. And so what does the area converge to? Well, the area converges to 2. The area under this curve, let me do the arrow here, the area under the curve is equal to 2. Okay, that area will be equal to 2. Okay. Even though it goes off to infinity, it basically this stuff over here doesn't matter, because basically you're adding on 0.0000000000001, right? As we get further and further here, the difference is so minuscule it doesn't even matter. Okay. That's the extra amount that I keep adding on. Okay. And when all said and done, it will accumulate to 2. Okay. Let's talk about a what's called a perpetuity. Okay, the accumulated value of, well, let's do present value. The accumulated present value of a continuous money flow into an account at the constant rate of P dollars per year. So I'm putting money P dollars per year, okay, perpetually. I'm just putting this in perpetually, okay, forever. Okay, and so the accumulated present value, okay, perpetually is given as the integral from 0 to infinity of p e to the negative kt, dt, which is equal to p over k. Okay, so if we do the integral here, okay, we would get this to be p over k. Why? Well, what's the difference here? The difference is that t goes to infinity, right? So p over k, right? This is very similar to the r over k that we had before. And then what was it before? It was 1 minus e to the negative kt, right? Kt. But in this case, what is t going to? T is going to infinity. Okay, t would be going to infinity. This would be infinity, right? So does this converge? Yeah, it does converge. 1 minus e, or 1 minus 1 over e to the kt, right? So what happens as this thing grows without bounds? This thing goes to infinity. Well, what's 1 over infinity? It's 0. And so what's 1 minus 0? It's 1. So it just becomes, this whole thing becomes 1 times p over k, which is p over k. Okay, so this whole thing becomes just p over k. It's just the first value. You could call it r over k if you really wanted to. If you want to call it r, just to, maybe we'll do r just to be consistent. We could do r over k, and then this thing just becomes r over k. Okay, that's the amount that's continuously being put in, and that's the interest rate. Okay, and that will give you the total amount forever. Okay, forever, which is the present value. Okay, so this is the present value. Present value of a perpetuity. Because it just perpetually keeps going and going and going and going. Okay, now perpetuity. Now there are certain perpetuities out there, but they're not as simple as this one. Okay, and we can talk about that in a second. The perpetuities that you really think of are just annuities. Okay, but they're just annuities that don't really ever run out of money. Okay, so say that you have a certain amount of money, right? Say that you have a certain amount of money that you start off with. We'll say 100 grand, okay, and you invest in it, and that investment makes over a year's period, it makes, or a 4-year period, however long you know, maybe over a month or whatever it is, okay, and then eventually you take money out of that, right? And then what do you want? You want that money to go back up so that you're never touching the principal, basically. Does that make sense? So you always want in the account the same amount of money. Okay, after my withdrawals. Okay, so that's just a different type of perpetuity here. Okay, it goes up and then we withdraw. That was kind of sucky. But it goes up and then we withdraw. And then it goes up and we withdraw. And it goes up and withdraws. It goes up and withdraws. And the more money that you have, the more you're going to be able to, withdraw. It's more interest. All you're doing is taking off the interest every month. Okay, and that's the type of perpetuity as well. Okay, but that's not the type that we're talking about here. Okay. Okay, this perpetuity looks like this. Okay, like that. And we just want to know if we keep adding money every year to this thing, how long you know, how much money, how much total accumulated value do I have there as this thing goes to infinity? Okay, present value. Okay, so for the present value is equal to R over K. Okay, and so let's do number 2 here. It says find the accumulated present value of an investment for which there is a perpetual continuous money flow of 2,000 per year. Ooh, nice. Per year. So maybe this is like interest you're making off and you're putting it into another account or something. Okay, per year at an interest rate of 5%. Okay, so continuous money flow, compounded continuously. It's also compounded continuously. Okay, so we're saying this is find the accumulated present value of this thing, right? So how much money do we have to start with to kind of prime the pump here? Okay, so continuous money flow of 2,000. Okay, so it would be, okay, 0 to infinity of P, okay, e to the negative kt dt is equal to P, or we could call this R again, R over K, right? R over K. So we're going to take our 2,000 and divide by 0.05, and that tells me that I would have $40,000 as my present value. Okay, that's my accumulated present value. Okay. Present value. Okay. Okay, so let me think about this for a second. Yeah, that's fine. That's fine. Because we're just saying that if we keep putting $2,000 in to this system every year, then present value, right? So if we put $2,000 into the system every year, right? $2,000 and it accumulates. Right? Just trying to think about what does this mean? Okay. And it accumulates. Let's see something for a second. the money flow is. Okay, accumulated present continuous money flow of p values that are constant from now until t years in the future, blah, blah. Yeah, of course we did. Okay. Because that's the accumulated value. But if we go out to t, right, then that's the accumulated value for decay. Right, but if we go out to infinity, then that's the whole thing. Okay, well, yeah. So we're just not stopping at t. We're not stopping at t for the accumulated present value. We're just keep on going to infinity, and that gives me the entire area under the curve. Okay, and so that's my total accumulated present value. From 0 to infinity, which means that the investment continues forever. It's behaving like it's going to continue forever. Okay, so this is the accumulated. That's not the present value. That's just the accumulated present value. Okay, that makes more sense. Okay. Okay, we'll stop there for today. We'll pick this back up on Thursday.